In the 1600s, Galileo discovered the iconic rings of Saturn, although he mistakenly labeled them as moons. In 1655, Christian Huygens discovered the first actual moon of Saturn, which is Titan. Over the next several years, more and more of Saturn's 31 moons were discovered. One of these was Tethys, discovered by G.D. Cassini in 1684. Tethys is a very unique moon in our solar system. It has an extremely low density of 0.98 grams per centimeters cubed. This is the lowest density of all major moons in the entire solar system. This indicates that it has a very special composition when compared to other bodies. A density of such a low value implies that it is made mostly out of water ice with a small portion of rock. The moon is 1,060 kilometers across, and its orbital period is 1.88 days at an average speed of 11.35 kilometers per second. Previous missions have been completed to learn more about the moon. The Voyager missions of 1980 and 81 photographed Tethys, revealing several characteristics of its surface, such as craters and surface ice. Although these missions were successful in their own regards, further information could be attained through a present-day operation. It is our intention to learn more about this unique satellite. In order to accomplish this, we propose the following mission, which will help us answer the subsequent research questions.
Is Tethys differentiated? What minerals are present on Tethys? What could have caused the Ithaca Chasma? And could the Ithaca Chasma and the Odysseus crater be related in origin? What is the topography like on the entire surface of Tethys?
The allotted budget for our mission to Tethys is $250 million, consisting of a fixed cost of $175 million and an instrument budget of $75 million. We will use our instrument budget to purchase the following instruments: a magnetometer, a high-rise class dual imaging system, and an X-ray spectrometer. The X-ray spectrometer is able to tell us what elements are present on the surface of Tethys. It is able to do this using natural X-rays from the sun reflecting off of the elements. The X-rays are able to reach the surface due to the lack of an atmosphere of the moon. The atoms of the element become unstable and begin to emit X-rays themselves. The X-ray spectrometer collects these X-rays in gas-filled chambers, and the X-rays are converted into voltages. All of the known elements have recorded voltages, so we will compare what we found on Tethys with what we already know. The magnetometer will be used in order to determine the magnetic field of Tethys. Using the magnetometer, we are able to determine the direction and magnitude of the magnetic field vectors. On top of being able to determine the magnetic field, it is also able to tell us if there are any metals deeper in the surface than we are able to detect with our other equipment. Magnetometers work by having a suspended magnet. When the magnet is in the presence of a magnetic field, the magnet is pulled towards the direction of the magnetic field. However, the movement is restricted by springs and the elastic fiber holding the magnet in place. The final direction of the magnet is something midway between the direction of the magnetic field and its original direction. The high-rise class dual imaging camera is a high-resolution imaging science experiment. This camera is able to take very clear photos of the surface of Tethys, roughly 1 foot per pixel. We will use this to photograph the rest of Tethys.
The target market for our education and outreach plan is for more students of all ages to become more interested in the knowledge of the universe. Most people don't know information about the universe, and especially Tethys. STEM is used for the general competitive education of the school systems in the United States. There has been a problem with the lack of people that are qualified in the high-tech industry, and it has been due to the lack of a curriculum in schools. This can be solved through the integration of interactive and interesting programs in the school systems. We will have an up-to-date website that changes with the new information and will make the students want to come back every day. A live feed of the instruments will make the students feel as if they are in the moment and are fueling the scientific discovery. Also, there will be expos and museums set up that move from city to city and suburb to suburb. This will be incredibly important for the underprivileged students that may not have access to the internet or proper education in their science class. In order to engage students at the expos and online, there will be different activities for the different age groups. For preschoolers and even elementary school students, coloring books are one of the best way to stay interactive. For middle school to high school students, there will be more in-depth presentation. These programs further the teacher's curriculum and help them engage their students in classwork and get them excited about homework. The budget for these expos and museums would come from the government for a return on investment. There would be more intellectual output in schools and more people willing to learn and attend college. This could also help unemployment because more people would be qualified for the careers that need to be filled and accomplished.